Yesterday, we were introduced to buffers. We learned that a buffered solution is one where if you have the solution and you add an acid or base to it, it resists changing pH by going through a special little process where it converts the invader into something that's already there. Now, while you learning what buffers was is essential, we're going to take a step back now. And what I mean is, anytime you have an acid or base solution and you invade it with something else, there's actually one of three different things that can take place. And your mission for the rest of this unit is to be able to identify, okay, there's an invasion happening. I've got my beaker that's been added some kind of strong acid or base. Which of the three things happened, and how do I handle those things differently? Make sure you have your slides out at home. I see these invasions as a war because the way that you're going to analyze which of the three things happens is like this. You've got the beaker that's already acidic or basic. Your job is to find what's the moles in there. You have one number. Then the attack happens. Either an acid or a base, strong always in here, is going to invade. But you need to know what's the moles of that. Now you've got two mole numbers. Now, whichever of those two has the higher mole count will win the battle. Whichever one has the lower mole count is actually going to disappear completely. But whatever that smaller number was, the larger number will go down by that much, as I'm about to demonstrate through examples. And then what you'll do is decide again which of the three things actually happened in front of you during the invasion. Y'all, this slide here is arguably not that one. I just forgot to show you that one at home. Anyway, this slide here is the most important slide for sure. Because when you do that moment where you look at the invader versus the original solution, only one of three things can happen. The strong invader can win. That's the best news. You're actually cheering for the strong invader to win because then it takes over the solution as a strong, which means negative log finds pH. Or the weak sample will win, meaning the invader wasn't strong enough to take over. The original is still there, and it's going to buffer. That's not such bad news. Depends on how you feel about yesterday. But it'll be the Henderson-Hasselbalch equation. Or, worst case scenario, there's a tie. If the moles of attacker is the exact same as the moles of the original, a tie leads to hydrolysis, which is just so much work. Fingers crossed that there's no ties. But I wouldn't give you a tie, because I'm not evil, right? Maybe. Of course, my job is to show you examples of each of them. So we'll see if we can identify what's happening, how to handle it, and get you some good notes. Are y'all ready? All right, let's take a look at our first invasion here. As I already said, our invaders will only be strong samples, which means even though it's going to look like an entire acid or base, you're going to need to identify it as a strong and then realize all I care about, all you care about for the invasion is always one of these two substances. All right? So maybe it's going to be hydrobromic acid, HBr. You know that's strong. So then it's just the H plus that's doing stuff. Or maybe it's going to be lithium hydroxide. You know that's strong. So it's just going to be the hydroxide that's actually changing the pH. There will not be weak invaders in this class. There can be weak invaders, just not in AP Chem. I'm going to draw a picture of just this first one. Just so we're all on the same page. If I take that problem and I imagize it, here's what it says is happening. there's a beaker. And inside that beaker, there is acetic acid. That's one of the items that's inside the beaker. Now, we have a shorthand for acetic acid that you are now allowed to use. It's HAC. Acetic acid is very commonly used in this, and so the shorthand helps out because acetic acid is an annoying formula to write a bunch. It's HC2H3O2. So acetic acid, weak acid, carbon containing. It also has acetate ion. It's hiding in salt, but the sodium parent is strong and spectates. These two things are in the beaker according to the wording of the problem. And then there's an intruder. It says that hydrochloric acid is going to intrude. HCl. I bring clay. Strong acid. So what do I really say is intruding? Hydrogen ion. Remember, it'll either be H plus or OH minus. This is what's happening. We have an established solution. We have H plus being dropped in. I want to know what happens afterwards based on the values. Hey, which of those two items is the hydrogen ion actually going to interact with? Yeah. So we know that that plus will be attracted to that minus. Here is the equation. Let's write it out. The intrusion is H plus. It's interacting with acetate ion. The yield sign will be a normally strong yield sign because it's always a strong invasion. That's good data to have. What's the product? Yeah, HAC, just like yesterday, in this buffered solution. Turns the invader into the other substance that's already there. Now remember, to figure out what's going to happen, I need moles of everything. Find the moles. Whoever has more moles is going to get rid of the smaller one and be reduced by that amount. How do we find moles? Well, we know that molarity equals moles over liters, which means if you rearrange that equation, moles is molarity times liters. So that's a handy thing to know because we've got those numbers. So here we go. If you look at the values, the invader is being described as 125 mils, which is 0.125 liters. Remember, we need liters in molarity to multiply, times 0.525 molar. If you multiply those together, you get moles. And in this case, for the H plus, I get 0.0656. If we head over to the acetate ion, you can find values for that as well. 125 mils. All right, so now we're dealing with this dude. 125 mils, which is 0.125 liters. But his molarity is 1. Of course, if you multiply those, you'll get moles of 0.125. There is given moles of acetic acid also. If you just read through the words, it lets you know that the HAC is actually present in those two pink values as well. So he is also going to do exactly that based on the given. And you've got this many moles of him. Everybody with me so far? We've just found moles of everyone. Who wins the invasion? Which of those numbers is the smaller number? Blue or pink? Blue is the smaller number. All right. So that's the one that's going to disappear completely. All right. It lost. So you're going to take the smaller number and get rid of it. The invader lost. But the other reactant will be reduced by that much. So we're going to subtract those moles because it was kind of a casualty of war type thing. And your leftover ion here is going to be 0.059. But keep in mind, as the reactants shift down, we've always known that the products shift up by the same amount. So this value will be added over here. Now, be patient with yourself. A lot of this is kind of new. It'll become repetitive through Canvas. But my products are actually going to increase up to a value of 0.191. The weak solution won. What does the slide before this one say we have to do if the weak wins? Buffers. It'll be a buffer. Henderson equation. And look, you can see that. That is a weak sample, and that is its conjugate. And they're both there. Now the Henderson equation will solve the problem. However, look here. The Henderson equation requires molarities. See that? Those have to be molarities. We have moles. It's easy to fix. It's also easy to forget to fix. To get the molarity that you need for the equation, it's moles divided by liters. So it's moles divided by, what's the total volume after the invasion? It's 250. If you look at the wording, 125 mils was dumped into 125 mils. 250 mils is the volume now. So we're dividing it by 0.25 liter. It's got to be divided by liters. And when you do moles over liters, you'll get molarity, which is what we need for our equation. And I've got both of those values. We've got 0.24 molar alongside 0.764 molar. Any questions so far? Now, since it's a buffer, though, we're ready to Henderson from yesterday. So here we go. pH equals pKa. P is negative log. Ka, it's up there, 1.8 e negative 5. Plus the log. Ion over weak. Hey, which purple number goes up top? 0.24. Just track it. That 0.24 is the ion. So 0.24 over 0.764. And boom, you're a click away from our first problem. What you think? Now, this is the middle type of problem. There's a worse one and a better one. But if the weak wins, this is what your work will look like. Yeah, yeah? Let's keep going. Oh, by the way, this 1.8 E negative 5, it shows up all the time. All right, you're going to get annoyed by it. It's because ammonia and acetic acid both have that K value, and those are very cheap substances. So in the real world, in labs, we use the cheapest substances we can because we never have money. Therefore, our examples tend to use those since it's real life. So that number, even though there's hundreds of Ks out there, you'll see that one a lot. All right, take a looky. It's a new one. What's the invader this time? Okay, but refine that. What's the real invader? OH minus. All right. The invader this time is going to be hydroxide. It's always either OH minus or H plus. No weak invaders. But this time it's a little simpler. I'm not going to draw it again. Drawing it's not part of it. I was babying you a little bit. But it's just being added to acetic acid. So this one's worded where you don't have to like say, oh, it's going to interact with this. It's being added to acetic acid. Normal yield sign. All right. Now, this is a Bronsted-Lowry association. Bases are proton acceptors, so the H plus moves over. That's going to give you aqua. Alongside, after the donation of acetate ion. To find the winner, we need to compare moles. How do we find moles? Moles is molarity times liters. Now, if you look at this problem, what is true about the volume and the molarity of both of these items? They're the same. So to find it, right, you need to go, what, 0.125, right? That's the liters times 0.5, right? You've got to multiply those, but we can already see that when we do, you're going to get the same number for both because they're the same. They're present in the same. So this times that is going to spit out 0.0625, but for both of them. Does this question list the starting amount of the acetate ion? It doesn't. Last time it did, so we put it in there. This time it doesn't, so there's none of it. Just follow the words. But what is true about those numbers being the same? Is it good news or bad news for us? God, it's such bad news. Like really bad news. If they tie, they're both going to zero out. Because remember, your job is to find the smaller number and subtract it. The smallest number is this number, which zeros them both out. But as the reactants shift down, what else happens? The products shift up by the same amount. The reason ties are terrible is because there's not strong to go negative log on. There's none of the weak, so the buffer is broken. All you have is this substance floating in the beaker. It's neither an acid nor a base. We describe it as the son of salt because it came from a dissociated salt. What's the only way to find a pH of salt? Hydrolysis. Now, I'm going to do this kind of quickly for time's sake, and you've already been tested on this, but still stop me if this causes you any problems. But we've got to do it. So, how do you do hydrolysis? Well, you take the weak sample and you add it to water in a rice table, keeping in mind that the K value is always wrong in hydrolysis, and we run through all those awful steps. So, let's hate each other. Here we go. I know that we've got to go rice. I know according to hydrolysis, the ion that we're dealing with will be added to water. It'll be at equilibrium because it's weak. That's interesting to remember. We've got to move an H plus, so this is going to move over to there, creating that and that. Remember, you are welcome to stop me if you need to. Do we have a concentration of AC minus? We don't. And this, I'll tell you what, guys, this is the biggest mistake I see, the most common one. The most common mistake, the most common mistake is not knowing what the heck you're doing. But if you feel like you know what you're doing and you're getting this, you will take that orange number and put it right there, and then you're wrong moving forward. Because you can't put moles there. Moles has never gone in a rice table. Concentration. To get a concentration, moles divided by liters. So what do I do to those moles? Well, divide it by the liters. 125 was dumped into 125 for a grand total of 250, which is 0.25 liters. Does everyone understand what I'm saying? Now, coincidentally, if you divide that orange number by that green number, you get 0.25, which is weird. But realize that this number is the quotient of those two numbers. But that is a molarity, and now we can keep rocking this. Shift reactant down, shift product up. I plus C equals E. We know that it's an equilibrium situation now, which is supposed to be K is products over reactants, but it's hydrolysis. We built a basic environment and all we have is Ka. We know that we must always fix the K, which is Kw divided by Ka equals Kb. So plug that in, and we get 1 E negative 14 divided by 1.8 E negative 5 given is going to give us a Kb of 5.6 E negative 10. They're allergic to awesome teaching. Are you with me? Products over reactants now that we have a proper K. So, we'll take that Kb of 5.6 E negative 10, set it equal to the products from the E row, which is a couple X's multiplied against each other, over that reactant. But we trump minus X as a denominator. Simplify, you'll get X squared equals cross multiply there. Square root to isolate. And now we've got an x value, but remember, it's only useful if we realize what the x value is. X is hydroxide. Which means, since we have a strong molarity, we just have to take the negative log of it, and it will give me, well, a POH because it's hydroxide. I get a pH of 9.08. Y'all are really, really quiet. Is that a bad silence? It's a ton of work. I mean, this is the hardest kind of problem I can give you based on where we are so far. So it exists, and I'm sorry. But the next one's the easiest type. Want to do the easiest type? Let's keep going. We all right? I think that you're going to work so hard on this for your Friday night instead of going out. Let's take a look at the next one. All right, we have another invasion. Hey, look, it's the same invader being dumped into the same thing, which is really nice because we're kind of already on the ball of what's happening. It says that sodium hydroxide, strong base, is being added to acetic acid. But we know what the Bronsted-Lowry looks like because we are rehearsed. What? Who's rehearsed? Somebody's rehearsed. Okay. Yeah, yeah. Same thing, but we need to know who wins by finding moles. So, if we go to hydroxide and we look at the values, this new one, did I show you? This new one is being given at 200 mils and 0.5 molar. All right, so we've got 0.2 liters then and 0.5 molar. So that's going to put us at 0.1. All right. The HAC, the acetic acid, is it's the same from the previous one. It's the 0.125 liters alongside the 0.5 molar. So again, multiply to find moles, and we will get that 0.0625 number again. Who wins? Yep, this bigger number wins, so we get rid of the smaller number. That's the bigger number, so we're going to reduce him to nothing and reduce him by the same amount, which is going to give me a mole count over here of 0.0375. Of course, as the reactants go down, the products go up. So we need to add that over here. Now, look here. This is important. You already wrote down what I'm about to say. I just haven't referenced it yet. When the strong wins, do you see how the strong won? Not only is it good news, but your brain is going to see that there is something else floating in there. Like there's this, but there's also some of that. Here's what's true. When the strong wins an invasion like this and it takes over the beaker, this ion only affects the pH about 1/1000th. So we don't care. A pH meter wouldn't even be able to read the acetate ion there. So, as is written on an earlier slide, if the strong wins, anything else in the solution is negated. Look what we have. Strong sample, negative log of a molarity. We don't have a molarity. It's easy to get. But it's got to be negative log of a concentration. Moles over liters. Moles over liters. What's the volume? Careful. 325. It was 200. They dumped in 125. 325. That's 0.325 liters. Moles over liters, in this case, will give you a molarity of 0.115. Watch what it is, though. It is hydroxide, so keep your notes clear. It's a strong, so it's just negative log. I get a POH based off hydroxide of 0.939. Now we can find an answer. I've shown you everything that can happen in an invasion. All right? A tie, a weak win, a strong win. Your notes has all of the routes. Now you just got to get good at it. To end today, what I did was I grabbed an FRQ from 2019, which is way more recent than the other ones I did that I grabbed for yesterday's lecture. But I thought it'd be fun to see if y'all would get the points. Do you think you could get these FRQ points? It's all about confidence. Way to go. Let's work them out together, though. All right. So 6 years ago, would you be able to use what you've learned in here to get these points? Well, part A is actually from several lectures ago. So let's see if you know what to do. It just says, what's the pH of a molarity of acetic acid? Acetic acid, that's a weak acid. How do you find pH of a weak acid? Add it to water in a rice table. But not only that, it's not hydrolysis though. Like, I think sometimes you forget that these used to be a bit easier than they've become. So watch, let's get the points for part A from last unit. What is the pH of a 2.0 molar solution of acetic acid? So what do? You add acetic acid to a rice table with water, equilibrium arrow, weak. Acids are proton donators, so the H plus moves over, which is going to give you acetate ion, and one of our best friends, hydronium. Right, water is liquid in a rice table. We do have a molarity given to us of 2. Shift I plus C. We have a K value for the sprinkle, but guess what? It's the correct K because it's not hydrolysis. So it's way more straightforward. Look, we built an acidic environment and we've got a Ka, so plug and go. The Ka, of course, is 1.8 e negative 5. K equals products over reactants from the E row. There's your 2 products. There's your reactant. But we trump minus X as a denominator. Simplify. You'll get X squared equals 3.6 C negative 5. Square root to isolate. Six E negative 3, it might say. But make sure you remember what X is, right? X hydronium, which again is good news. Everything is lining up for us. Because now, since this is a hydronium concentration, which is strong, negative log will give you the answer. It'll spit out pH. So we just have to go negative log of that number. Could you have gotten that first point without me? I hope so. You should have been able to. That was from last unit. Hey, guess what? Part B is an invader. Hooray! If you look through Part B, Here's what it says. It says sodium hydroxide. Is it sodium hydroxide? Yep. Sodium hydroxide, strong base, gets dumped into acetic acid. Strong base gets dumped into acetic acid. Y'all, this is the third time we have written this association. All right. So if nothing else, if you're bad at Bronsted-Lowry, at least memorize how this interaction works. Here we go. It's an invasion. We got to know who wins to know which of the three things is going to happen. Molarity times liters. All right. So if you look at the hydroxide values, you'll see that it's given at 0.1 and 1. 0.1 times 1 is 0.1. And it's already in liters this time instead of mils. That's nice. If you look at the HAC, molarity times liters, it's given at 0.1 and 2. Multiply them to get that. There is no acetate ion mentioned at the beginning. Who wins? HAC, which isn't the best news, but it's not the worst news. At least it's not a tie. Find the smaller number and get rid of it. The invader lost. But there's leftovers of the weak. The weak won. But as the reactants shift down, the products shift up. What chemistry happens when the weak wins? A buffer. Your notes say so. It's a buffer. Because look, there's a weak sample and its conjugate, so it's Henderson. But you have to have molarities, right? Henderson requires concentrations. To find concentrations, we know that it is moles over liters. We've got moles. What's the liters? Well, if you look, it's 0.1 liters. With 0.1 liters is 0.2 liters. When you run those, the molarity that you get will be 0.5. Now we're Henderson ready. Here we go. pH equals pKa. P is negative log. Ka was given at the previous part of 1.8 e negative 5. Henderson equation plus log. The concentrations are the same, but which one would go on top? AC minus, right? It's always the ion, but they were pretty nice this year. And that'll give you a pH, which feels like a good moment for this your weekend getting near. Except, what's it asking for? Yeah, look, there's the twist from this year. Because a lot of students just submitted the pH because that's what they were so trained to do, right? If you run that, it's going to spit out a pH of 4.74. And then, surprise, surprise, this question's not asking for pH. It's asking for hydrogen concentration. Such an easy fix, though. Such an easy fix. What do? Just 10 to the negative. 10 to the negative pH solves your problem. 10 to the negative 4.74 gives you a coincidental answer of 1.8 negative 5. Yes. It'll never be 1/6. Oh yeah, you're right. Yeah. Well, but did you see the green? I put green fonts below them to try to expand out. Like that's it for y'all. Now they're just